Excellent. Thanks. Okay, good morning, future presidents. Good reaction this morning. Okay, so guess what? It is that time again. We are quickly approaching the end of the semester. So midterm number 2 is a week from Thursday in class. We are covering material up to electric circuits, which is what we are covering today. So today's material will be the last material on the exam. I'll primarily be focusing on chapters 4 up through the material today. So that doesn't mean there won't be anything about chapters 1 through 3 on there. That means, momentum, energy, those concepts are sort of fair game, but they will not be the focus of the exam. So, but you're certainly expected to know those concepts when answering more advanced concepts. So that's the material. The practice midterm will hopefully be up today. I'm having somebody proofread it to make sure I didn't make any really silly mistakes on there. So the practice midterm should be up today, and there is a review this Saturday from 10 to 12 in 155 Dwinell. So this material should all be on the course website soon. So, okay, let's see. Any questions about the midterm before we go on? The format will be identical to the last one, so shouldn't be no big surprises on that. Okay, good. You guys are ready. Let's do it today. I got it here. Okay, so let's continue on where we started last time. So last time we introduced the concept of electrical voltages and electric charges and the electric force. And today we're going to talk about electric currents and electric circuits and how we use those. So last time we saw if we actually physically separated positive and negative charges, we gave those charges a new type of potential energy, electrostatic potential energy. Oh, yeah, sure. Wei, can you turn the volume up some on this? Okay, is that better? Yeah, okay, great. Thanks, guys. So last time we saw that if we physically separate charges, electric charges, we could basically store energy as electrostatic potential energy. Okay, so here was the picture we had. We had two plates of material, one of which we charged, we moved positive charges onto, and the other one had negative charges. So when we physically separated them, we discussed how we have to do work to physically separate them because they are attracting each other. So we are storing energy in this configuration. We defined the voltage across those two plates. The voltage is equal to the potential energy per charge. Okay. So it's the amount of potential energy stored in that configuration per unit charge. And we discussed briefly about how we could recover this energy. It's the same thing for gravitational potential energy. Remember, to cover gravitational potential energy, if we lift an object up, we give it gravitational potential energy. And to recover it, we let it drop. Okay? Same thing here. To recover this potential energy, so we have positive charges here, negative charges here. They're separated. In order to recover it, we need to have charges that actually move between the plates. So either positive charges move down to the negative plate, or negative charges move to the positive plate, or some combination of the two. So to recover that energy, we need to get a charge transfer between those two plates. So this, of course, is a very convenient way that we use energy in the world around us. Okay, voltage allows us to do work. There are a lot of practical applications about in the world around us how we convert electrostatic potential energy into useful forms of work. So let's look at some of those. First off, let's just talk briefly about some of the ways we access electrostatic potential energy, okay, one of the most common is batteries, of course, where batteries are using chemical potential energy and converting that into electrostatic potential energy, which we use for work. So batteries we can think of as just a chemical charge pump. Okay, so where they use, where the chemicals store energy, so chemical potential energy, which we've talked about before. Okay, so the chemicals store energy, and that is converted to voltage, which we use. Okay, so here's a picture of a battery, not a great battery. Okay, so batteries, the way they work is that there is a terminal here, the little knob on the top, which is where the positive voltage is, or where the positive concentration of charges are, and the bottom is where the negatives are. Okay? And there is a voltage difference across there, and the typical voltage difference is on the order of a volt, or 1.5 volts for a battery like the one I drew here. Okay, so that is a typical voltage for a battery, okay, relatively small voltage. Okay? And literally the chemicals in the battery, they literally pump positive ions. So remember, an ion is just an atom that has had its electron stripped off. So you take away the electron, and you're left with a positively charged atom. So it literally pumps ions up to the positive terminal, and electrons down to the negative terminal. Okay, so and a battery has a certain amount of energy which is stored in the chemicals, and that's the amount of energy that we can access when we're using the voltage to create electrical currents. Okay. So that's about all we're going to talk about batteries. The book goes into a little more detail, but that's all we really need to know, is that it's a voltage source and has a finite amount of energy that we can access. Okay, the other common way is electrical outlets. Okay, electrical outlets. Let's see if I can draw electrical outlet. There we go. So, electrical outlet usually has multiple terminals and the little ground there. So, literally, this has a voltage difference between these. Which is about 120 volts, so significantly larger than what we get out of the battery. Which is why we have to be a lot more careful about the electricity we use when it's coming out of the wall. And it has a ground, okay, which is just a safety feature. It's quite literally connected to the earth if it's wired properly. Okay? And the ground is designed to keep the keep you and the socket at the same voltage. Okay, So that literally is saying, it's trying to keep this whole fixture, the outside of the fixture, and you at the same voltage. Otherwise, every time you plug in a light, and you might have done this sometimes if you've ever plugged in something that wasn't to a receptacle that wasn't properly grounded or properly wired, and you get a current that starts flowing between you and that. Okay? That is always a little scary. When you plug something in, the current starts flowing. Yeah? Sorry, can you speak up just a little bit? So the question is, does this depend on the appliance that you're plugging in? And, and, and do you get more shock depending on what the appliance is? Well, appliances definitely, and TV is one, but definitely old TVs especially, where they build up a lot of charge inside, and you can get a shock when you are plugging that in. But that's a little bit different than here. So most modern devices have the 3 prongs because they're trying to keep the device at the outside of the device, the case of the device at the ground as well. So a lot of older appliances don't have this 3rd prong here, right? And so that means that the outside of the appliance can get charged up. You can get a positive charge, and then when you touch the appliance, you can get shock. So yeah, so this is definitely a much safer configuration. And it does. Some appliances will naturally just build up charges. Old TVs are sort of notorious for that, building up very large charges. And this is designed to keep that, off of the case so that you don't shock yourself just by touching it. Yeah, that's a great question. So, any other questions on that? Yeah, okay, so, and then the third I just wanted to point out here is not as common, but becoming more and more so. Which are solar cells. Okay. These are becoming more and more common in everyday usage, I'm glad to say. So solar cell works through sort of complicated physics, which we won't discuss in too much detail. It's what's called a semiconductor. And these have the interesting property that when light is shined on them, so especially sunlight, which is free, they act basically just like a battery. They start working like a charge pump, and they create a positive voltage and negative voltage difference. So there's a voltage difference that develops across the terminals on that solar cell when we shine light on it. Okay? And from that voltage difference, it means there is potential energy there that we can use. So it's literally converting light directly into electrostatic potential energy. So let's see, I have a couple of solar cell demos here. So here is a cool solar-powered helicopter. Let's see, there we go. So this is a little solar cell here. And when I shine a light on it, woo, that's bright. You guys can see that. Don't want to shine this right in your eyes. Okay? You can see that it is basically just converting that directly like a battery into it. Okay? Let's look at the voltage on this. This is a very similar solar cell right here. And I've got a voltmeter hooked up to it. Let's see. I'm just going to shine the light on this, and we can look and see what the voltage is. I don't know if that shows up at all up there on the screen. Let's see. I'll just talk through that then. Okay, so right now you can see that this is measuring 0 volts here. Yeah, there we go. I don't know if you can read that or not. So I'm just going to shine this light right on it. Okay. And you can see that it has jumped up to a little over 3 volts. Okay, so a small, not too powerful battery. Okay, that's why we need a lot of these together in order to produce a significant amount of power. Okay. Turn the light off, you can see the voltage drop. So, very useful property of these semiconductors, okay, to be able to convert light directly into voltage, which we can convert into work very easily. Okay. It's not the only way we can convert light into work. Okay? So we're going to talk about that a little bit next Tuesday, about light and different ways we can use it to produce energy. Okay? But solar cells are certainly one very convenient way to produce electrical energy directly. Okay, so we've already said for this voltage difference across those plates, we've got electrostatic potential energy. In order to get that energy back, to recover some of it, we have to let charge flow. So for a voltage source to provide power, okay, charge must flow between the positive and negative voltages. So this is what we call electrical current. Okay, it's just a flow of charge per unit time. So current is charge transfer per time. Okay, so it's just a charge per time. And when we want to get useful work out of these charged plates, for example, a battery or your wall socket, then this differs a little bit from gravitational potential energy because, remember, there are two charges, and they can attract or repel the electrostatic force. But that means that the electrons on this plate are attracted to the positive plate, and the positive charges on this plate are attracted to the negative plate, which means we can get work out of this system by having either positive charges transfer down to the negative plate, or negative charges transfer up to the positive plate. Both of those charge transfers will release some of the energy from the electrostatic potential and convert it into kinetic energy of these charges, which we can use for doing work. Okay, so here is the, so let me put some labels on here. This means there's a voltage drop across here, okay, and this shows a current flowing. Okay, so now one thing to keep in mind, because these have different signs and they're flowing in different directions, they actually define the same direction for the current flow. Okay, so let me draw a picture of that. So let's say we have a wire here, which we're using to connect those terminals. And this is a slightly unconventional wire in that it has positive charges flowing. Okay, so if we had a positive voltage here and negative voltage here, we would have the positive charges flowing naturally to the right, okay, picking up, converting that electrostatic potential energy into kinetic energy. Okay, and we would define the current flow as being in the right direction. So that's the direction that the positive charges are being transferred. Okay. Now, if we have what's really going on in most wires is that we actually have electrons that are moving. So negative charges, once again, we've got the positive voltage here and the negative voltage here. Okay. So the electrons are attracted to the positive voltage and move to the left. Okay. But we have a negative charge moving in the opposite direction, which means when we take into account the sign, the current in this wire is still defined as being to the right. Okay. Negative charges moving to the left is the same as positive charges moving to the right when you're talking about the current flow. Okay? So the direction is opposite the direction that the current is defined as flowing is opposite the direction the electrons are actually moving. Okay? And as far as the work that's produced or the work that is released, this configuration, it doesn't actually matter whether we've got positive charges flowing to the negative or negative charges flowing to the positive. Okay? As long as we've got that charge being transferred and picking up that voltage difference, the electrostatic potential energy per charge, then it doesn't matter which way that's going. Okay? In the real world, in most wires, we have electrons flowing, which means the electrons are actually physically moving the opposite direction that the current is being defined as flowing. Okay, so these are blown up pictures of wires, and that's how we usually, in most circuits, get the energy out of a voltage difference, by letting current flow through conducting wires. And current flowing through wires defines what we call electrical circuits. Okay, so in most practical applications where we're trying to get energy out of some voltage difference, whether it's a battery or the electrical outlets or solar cells, okay, we have to let current flow, and current is usually confined to flow in wires. Okay, to whatever appliance we're trying to power. So wires are just a very convenient way of allowing charge to flow, and it also means we can control where the charge is flowing, okay, which is important for not just safety reasons, but for, actually getting the energy out and putting it where you want to. So current is usually confined to flow in wires, and this is just what we call a circuit. Okay. Circuit is a path for current to flow in order to get useful work out of it. And one of the simplest examples is just a circuit for a flashlight. Okay, so for example, you could have a battery powering a light bulb. Okay, so let's just draw a picture of what that might look like. So there is our battery again, drawn from the side. This has got a positive terminal and a negative terminal, which defines the direction of the voltage. Okay. And when we want to power a flashlight bulb, we would attach a wire to the positive terminal. Okay. That flows through, that allows current to flow through that light bulb, okay, and then the current returns back to the negative terminal. So in this picture, we've got our battery, we've got our wire, which of course is a good electrical conductor, so the charges can flow very easily. We've got current flowing. Okay. We draw it always from the positive terminal to the negative terminal, even though in reality it's electrons flowing in the opposite direction. Okay. And those are transferred through the bulb, which produces the light. So it's converting that electrostatic potential energy into light and heat, depending on the type of bulb that it is. Okay, so, and then at this point, the current doesn't stop here. The current keeps flowing around. Those electrons have to go somewhere. So they're not building up in that light bulb. Otherwise, the light bulb would be getting a big charge, right? And as it grows up and as it gets a bigger charge, the forces of the electrons in there would get very strong, and they would be repelling any other electrons that are trying to come in. Okay, so the fact that we're using the energy doesn't mean that the electrons are stopping here. Okay? They're just transferring their kinetic energy into that bulb, okay, for to be used to produce light and heat. Okay, and so that's how we deliver power to that light bulb. Okay, so an important point, which I was just trying to make, is that in order for the current to be able to provide power to this light bulb, there has to be a complete circuit. Okay? Current is flowing in, but it also has to be able to flow out. If it weren't able to flow out, then this bulb would just be getting a big charge on it. Okay? And remember, light charges repel. So if this started building up a big charge, it would just be pushing back all that current that was trying to get to it. Okay? And so it wouldn't let a current flow. And if a current's not flowing, then there's no energy that's being transferred here. Okay? So in order for power to be transferred in a circuit, electrical circuit, we need to have a closed circuit. There needs to be a complete path for the charge to flow from the positive voltage to the negative voltage. Okay. So let me write that down. So for current to flow and transfer energy, we need a complete circuit. Between the positive and negative voltages. Okay, so if we have a complete circuit, we have a name for that, which we call a closed circuit. Same thing, closed circuit is just a complete circuit. It means that there is a full path between the positive and negative terminals for that current to flow. Okay? Otherwise, the current can't flow. It will just build up some charge in here, and then it'll stop any other current from flowing. Okay, so we need a closed circuit for that. If it's not a complete circuit, then charge will not flow. Let me draw a picture of that. So here is our battery again. It's got a positive terminal and negative terminal. We're going to have the wire comes out and goes to our light, to our bulb. Okay? But there is no wire coming off that bulb, so it's not a complete circuit. There is no path back to the negative terminal. Okay? So for this configuration, we call this an open circuit. Okay? And in this circuit, there is no current. Can flow. Okay? And that means there's no light and no power transfer. Okay, so not unless we add another wire to this circuit, allowing the current to flow back to the negative terminal, will we get a current flowing through that. Okay, so this is an open circuit, and no more power can be delivered through that. Okay. Now, there are good reasons to actually design open circuits. For example, let's draw the flashlight circuit one more time. There's our battery with the plus and minus terminal. And there's our wire coming out. And we're going to put a gap in that wire. And there's our bulb. And there's a wire going back to the bottom. Okay. This, in this configuration as we have it, there's no current flowing because these wires aren't connected. But that's why we put a switch across there. This is just like the switch on your flashlight or the switch on the wall, okay, for lights in your room. Okay, and the simple idea from that switch is when we close the switch, we form a closed circuit, and the current can flow. Okay, when we open the switch, we form an open circuit and the current can't flow anymore. So we're basically just turning it off and on. So open switch. Is an open circuit. Okay, and you can see from the idea of a switch where these terms closed circuit and open circuit come from. Open the switch, close the switch. Okay, so this is just the basics, very basics of circuits, okay? But you need a closed circuit for this current to flow, and without a closed circuit, then you don't get current flowing. That's also why when people are working around voltages or high voltage sources or some sort of current sources, usually wear rubber-soled shoes. Okay? That's because those are very poor conductors, which means that if you touch something that's a high voltage by accident, then current is not free to flow through you because it has nowhere to go through your feet. Okay? Whereas if you're barefoot and touching the ground, or if there's water around, good conductors, then current can flow. Okay, so with rubber shoes, you're a good open circuit. Okay, so that is our circuit. Now let's talk a little bit about the power that's being transferred. Okay. Remember that electrical power, let me just write this section here. So electrical power, so voltage is equal to the potential energy per unit charge. Okay. So that's amount of energy that each unit of charge would have if it were allowed to go between the terminals, between the positive and negative terminal. And current is equal to the charge transferred, or how much charge is flowing per time. So it's the time rate transfer of charge. Okay. So if we want to know the total power that is being delivered by a voltage circuit, so this is the amount of energy per charge, and this is the amount of charge per time. Remember, power is the energy that's transferred per unit time. Okay. So we get a very easy relationship from those two, which is the power delivered is just equal to the voltage, the energy per unit charge, times the current, which is the charge per unit time. So the power being delivered by a circuit is just the voltage times the current, right? It's flowing out of that voltage. So once again, it's the energy per unit charge times the amount of charge per unit time, which gives you the energy per unit time that's being transferred out. Okay. So when we have some voltage source, whether it's a battery or a wall socket or our solar cells, then put that in a circuit. The simple picture is that we've got some source of power or voltage. So there is our voltage source. So that, once again, can be a battery, or it can be our wall socket, or it can be the solar cells, or there are other choices. Okay? So there is our voltage source. It is connected by a circuit to some appliance. Lots of different appliances, so we'll just call it stuff. Stuff we want to power. Okay? And then it's connected back by wires to close a closed circuit, okay, around that. A closed circuit so that current can flow. So we've got current flowing. It has to flow into whatever we're trying to power and back out of it so that we don't get any charge buildup in that. Okay. And the fact that we have current flowing from a voltage source, okay, means we're delivering power. So we're delivering power to this appliance, whatever we're trying to run there. Okay, so for one example of this are batteries. And batteries, when you go to buy batteries at a store, you'll see that different batteries and different types of batteries have different voltage ratings. Okay, so they have, some of them have 0.7 volts, some of them have 1.5 volts. Okay. The voltage rating doesn't tell you how much energy is stored in the battery. The voltage rating just tells you how much energy per unit charge would be delivered. Okay. So the different batteries, so a battery has a fixed amount of energy that's stored into it, and how long that battery lasts will depend on how much current you're pulling out of it. Okay. The voltage isn't changing, it's the amount of current that you get out of it. Okay. And the more current you draw out of it, the more power you use, which means the shorter the battery's lifetime will be. Okay, which I think is pretty intuitive. Okay. So when you're looking at batteries, there will be a rating on that, which is not the voltage, but it's the voltage times the current. So it's usually a voltage times a number of amps per hour or something like that, which will tell you how much total energy, and then the time, which, so it's a power times the time, which tells you how much total energy is stored in the battery. Okay, so the voltage doesn't tell you the total energy. It just tells you how much is transferred per charge. Okay, so one question about this picture, or maybe about the light bulb, would be if we take that battery and we connect it up to a light bulb, okay, why doesn't that battery just instantly transfer all of its energy to the light bulb? Okay? What actually limits the rate that the current flows? So, so there has to be some physical property of the system which keeps that battery from instantly dumping all of its energy between the terminals. Okay? And that property is given the very appropriate name, which is resistance. Okay, resistance is the property of circuits or appliances which limits the amount of current flow through a circuit for a given voltage. Okay, so once again, same picture. We've got our battery there. It's connected to our light bulb. Okay. That battery has a voltage across it. So there is current flowing. through that circuit. Okay? It's flowing out of and back into our voltage source. Okay? Power is being delivered to that light. But there is a limitation on how much current can flow through this circuit, and that limitation is set by this property that we call the resistance of that light bulb. How much it is resisting the flow of current. Okay? It limits the rate that power can be delivered down there. Okay, so let me say one word here. The idea that we are transferring energy through this current to this light bulb, we often talk about the voltage drop. Okay, the voltage drop tells us how much energy is being transferred per charge to that light bulb. Okay? The battery is providing a voltage, okay, and then the light bulb has a voltage drop, which is the fraction of that energy that is being used up in the light bulb. Okay, so resistance, very simple concept. Okay, to understand, when you understand that current is actually charge physically flowing. Let's see. Wei, can you come over here and zoom in on this? Wei? Are you there? AFK in the booth. Hey, Wei. Yep. Never happened. This never happened before. Okay. She must have stepped out for a second. Okay, so here is our model of a wire. Okay, so the wire has got current flowing through it. Okay. There we go. Okay, thank you. Excellent. Okay, so here's our wire. Okay, so what I've got here is a bunch of nails that are stuck in this board. Okay, those represent atoms. Okay, atoms inside this wire. So, for example, most wires are made out of copper. So these would be copper atoms. Okay, and we're just going to let our electrons in the form of marbles flow down this wire. Okay, and what happens when an electron tries to flow? Okay, it starts hitting all those atoms in its way, right? So there is a resistance for that electron to flow along the length of this wire. Okay, so in this model, right, the fact that there is a height difference between the top and the bottom is a gravitational potential energy, which is the same as our voltage electrostatic potential energy. Okay? And the electrons, when they flow, are moving down. Now, a couple things to keep in mind in this picture. This is actually a very good picture for electron flowing, is that there is potential energy here, okay? And that potential energy is being converted into kinetic energy, okay? But there is a fixed time for these electrons to flow, okay, which is set by the fact that they are constantly transferring that kinetic energy they're picking up to the atoms that they are running into. Okay? So those atoms that are in the way of the electrons flowing are providing a resistance, which are limiting how fast that they can flow, okay, down that wire. Okay? So same thing is happening in electrical circuits. Okay? There is a limiting rate that the charge can flow, and the energy, okay, when the current is flowing through a resistor like this, a circuit that is providing a resistance, the energy of the charge is constantly being transferred to the atoms, okay, through those collisions. So even though they're flowing, their kinetic energy is not getting arbitrarily high, because every time it picks up, it gets transferred to when the atom's there. So that means that the energy is getting dissipated in these atoms along the path. Okay? So the resistance is providing a way of dissipating that kinetic energy, okay? And that would form either hopefully as light or heat in case of a light bulb, or just thermal energy if it's being dissipated elsewhere in the circuit. Okay, so that is the resistance, okay? And there is an empirical relationship between the amount of voltage and the amount of current that can flow. And that is probably not too surprising. So remember, voltage is potential difference. Okay? So same thing as our gravitational potential energy here. And you can imagine that, let me adjust this a little bit. The current is how fast the charge is flowing. Okay? And it's pretty easy to imagine that if there's a small potential difference between the ends here, that the current is going to flow really slowly. Right? And if there's a high potential difference, then the current's going to flow much faster. Okay? So the higher the voltage difference across this resistance means the faster the current's going to flow. Okay? That is a empirical relationship between the voltage and the current, which has a name called Ohm's law. Okay, so Ohm's law is just an empirical relationship, which we just saw there, between the voltage drop and the current. Empirical just means we measured it. This is measured in the lab by Ohm. Okay, so remember voltage drop. So this is a term we're going to use. You'll hear frequently. So voltage drop is a little different from the voltage provided by the battery. Voltage drop is how much the voltage is dropping across this resistance, or across this light bulb, across your toaster, across your laptop. This voltage drop tells you the amount of energy per charge that is getting used in this appliance, okay, as opposed to the amount of energy per charge that's being provided by the battery. Okay? And the reason is you can have, you might have 2 light bulbs on here, okay, in which case you've got half the voltage drop across one and half the voltage drop across the other. Okay, so voltage drop tells you how much it's dropping across a particular piece of the circuit, in this case the light bulb or the appliance. Okay, so Ohm's law, very simple, just tells us that the voltage drop is equal to the current times the resistance. Okay. So that is the empirical relationship, or we can turn that around and say the current is equal to the voltage drop divided by the resistance. Okay, so this one is, the second one is maybe a little more intuitive to understand, okay? Which tells you that the amount of current that is flowing through this resistor here is going to be higher the higher the voltage drop is. So the higher I pick this up, okay, the faster the current can flow through there. So the current is proportional to the voltage drop, and then inversely proportional to the resistance. So the more nails I have in here, so the larger the resistance is, so the more atoms that are in the way, then the lower the current is going to be going, just because it will flow slower. Right? So the more stuff is in its way, blocking its path, the slower it'll flow on average. Okay, so very simple relationship between the amount of current that can flow in part of a circuit and the amount of resistance that's provided by the circuit for the voltage drop. Okay, so as we already said over here, when there is a voltage drop, okay, so imagine that we've got this charge that's flowing through this resistor. Okay? When it's flowing through there, its energy is getting dissipated. Okay? So the amount of voltage drop across here is telling us how much energy is being dissipated by that marble as it's falling, or by the charge as it passes through there. Okay? So that amount of resistance limits how much the current flows, which tells us how much power is being delivered, okay, to that part of the circuit. Okay? So that power is being dissipated by the resistance in that circuit. Okay, so that's an easy relationship. We already know that power is a voltage times a current. So this relationship you should be thinking about as how much power is being delivered by the battery. So there's the voltage of the battery times the amount of current that is being delivered to the battery. Now, in terms of the amount of power that's being consumed within that appliance or within that resistance, okay, so the power consumed in the resistor So the power consumed is just going to be equal to the amount of voltage per charge that is changing across that resistor. So that's the voltage drop. Okay, that tells you how much energy per charge has been dissipated across that resistance. Okay, multiplied by the current that's flowing through it, the amount of charge per unit time. Okay, so that is just the power consumed, the voltage drop across the resistance times the current that's flowed. Now, though, we have a relationship for the current and the voltage drop. The voltage drop is equal to the current times the resistance, right? So we can plug that back into here and say the power consumed is equal to the current. So the voltage drop is the current times the resistance. And we have another factor of the current that's coming in from here. So the amount of power consumed is going to be the current squared times the resistance of that circuit. Okay? That's how much power is being dissipated in this resistor. Okay? And this comes from the fact that power is voltage times current, and we have this empirical relationship for a given resistance between the voltage and the current. Okay? So it goes as the current squared times the resistance. Okay? And that power is being dissipated in the circuit. Let me bring this down. Let's see, Wei, can you focus in on this section of the bench for the next demo? Oh, sorry, wrong one. It's this one. Okay, so all I've got here is a very simple circuit. Let's see. On this one, let's actually focus down on the table here if you can. Let's see, right here where I'm pointing. There you go. That's great. Okay, so all I've got here is a very simple circuit which just has a wire running to electrical outlet, and it's running through up to the switch. So right now the switch is open, which means there's no current flowing, which is good because this is plugged directly right in the wall. This runs to a piece of wire here, which is just offering a resistance, and then back down to the wall. So right now, all I've got in this circuit that is limiting the current flow is this little piece of wire right here on the desk. Okay? So wire, we know, doesn't have a lot of resistance. That's why we use it to transfer charge. So when I close this, let's see. First off, we've got a current meter here. So when I close this, you're going to see the current jump up. Okay? And remember that current is delivering power. Okay? The voltage is 120 volts in the wall. The current is going to be running through this wire. And when I close this, you're going to see the current start to pick up there. And that is transferring all of that energy, the only place it can, which is to this little resistor. And it blew it. Okay? So this is how a fuse works. In the fuse box, for example, the old-fashioned fuses, is that literally just a piece of wire, which is, when it gets too much current flowing through it, it heats up. Okay? It heats up and it melts. So I literally vaporized this wire here. And if you're up here, you could smell it. It really stings from vaporizing that. Okay, yeah? You're right. We're going to get to that right now. So there are other wires in this circuit that are actually offering resistance as well. So you're right. So there was current flowing through all these wires here. So but their resistance is even lower than that. So to first order, we could ignore the resistance in the wires, but not always, which is what we're going to talk about in 1 second. So yeah. Yes? So voltage and voltage drop. So the difference between voltage and voltage drop. So they're both voltages, but you should be thinking about, whenever we talk about voltage, we're usually talking about the source. So like the battery or the wall. So this is how much energy per charge is being delivered in a circuit. Whereas the voltage drop is usually how much energy per unit charge is being dissipated in whatever you were powering. So when we talk about voltage, you should be thinking about the source. And by voltage drop, you should be thinking about where that energy is being dissipated. Okay? And it doesn't have to all be in there. Some of it can be in the wires, which is what we're going to talk about in 1 second. Question. So let's see. Any more questions on this? Yeah. Oh, no, you're just stretching. Okay, great. So, wow, you anticipated my next topic immediately, which is, in all of these previous pictures, we basically ignored any resistance in the wires. Okay? So we had all the energy being transferred to our appliances, and we ignored the fact that the wires themselves have some resistance, okay? Which means that there is a voltage drop across them, which means that there's power being dissipated in the wires. And we just saw that dramatically here, okay, where we saw the power being dissipated in this little section of wire, but power was being dissipated all throughout this system. Make sure I turn that off. Yep. Okay, so let's draw our picture again, but this time a little bit more realistically. There is our battery with plus and minus voltage. There's going to be power that's being delivered to some source, in this case our light bulb. And so there's current flowing into and out of that. And we were just talking about the resistance of, for example, the light bulb and how that dissipates power. But in reality, there is resistance in these wires as well. So in this case, we'd have, for the wires, we'd have a small resistance. Which will lead to a small voltage drop across that wire. Okay, so some fraction of the energy per unit charge is actually dissipated in the wire, okay, while it's sending current here. And then we'd have hopefully if you've designed a good circuit, we would have a large resistance, a large voltage drop. In whatever appliance that we are running. Okay? So we want the bulk of the energy per unit charge to be dissipated in our appliance and not in the circuit that is running to it. Okay? And then finally, the current is flowing back. So once again, we have a small resistance. And a small voltage drop. In the wires that are running back. Okay? So, whenever we have a real circuit, there's going to be some energy that is dissipated in the wires. So some amount of lost energy that is dissipated as heat in the wires, and that's energy that we can't recover. Okay? So, you can think about how we could limit that resistance. Okay? So there are two ways to limit the resistance of the wire, and you can think about our model here to think about how that might be. The two ways to limit the resistance in the wire is, the first one is to just make them really fat. The bigger the wires are around, okay, the less resistance they're going to offer. There's more paths for the charge to travel through. Okay, so to decrease the resistance, we can make the wires thicker. Which just gives more paths for the charge to flow, so there's not as many conflicts there, and it can flow easier. Or we can keep the wires short. Okay. If you have a really long wire, it's going to dissipate more energy. It's going to have more voltage drop than a very small wire. Okay, just because there's a longer path for that charge to interact with stuff in the way and dissipate its energy. Okay, two ways to decrease the resistance. Okay. Now, and remember that the power lost is going to be equal to current squared times the resistance, okay, in that section of the wire. So when we're delivering a certain amount of current, okay, the smaller the resistance of the wire, so either the bigger the wire is or the shorter the wire is, then the smaller amount of power is going to be dissipated, okay, in the wire. Okay, so let's think about how we actually get power from power stations. Oh, I probably should have kept this one up, but okay. Okay, so let's think about power plants. Okay. These are factories that are actually producing the electrical power that's delivered to us in our wall circuits. Okay. So, power is delivered to us through transmission lines. You see the big cables that are usually running along streets. And there's 2 points we need to keep in mind in this picture. So, first is that power lines, which are just wires, okay, are very long. Okay, you don't want a power plant sitting next door to you. Not a very attractive neighborhood. So power plants are usually located tens to hundreds of miles away from where they're delivering it to a city or to homes. So the power lines, the wires that are delivering that power are very long, which means they potentially have very high resistance because the length is so long. And the other thing we want to keep in mind is that most of these are made out of copper. And copper is expensive, okay? Maybe not if you're, building a little copper bracelet or something, but if you are spending, building wires that are hundreds of miles long, you're talking about many, many tons of copper, which gets to be very expensive. Okay, so let's draw a picture of our power plant. Oh, by the way, that second point, the copper is expensive, means that we don't necessarily want to just build thicker and thicker transmission lines to deliver power to our homes, okay, because that can be very expensive, building thicker and thicker copper lines. Okay, so let's draw a picture here. Here is our power plant. And that power plant is literally delivering a voltage drop across our lines, okay, which are coming into our homes here. We have current that is flowing through those transmission lines. Okay, and the voltage times the current will tell us how much power is being delivered from that power plant. Okay, and that's hopefully being delivered primarily to the user or to our appliances. But we have to keep in mind that there is a resistance in these transmission cables, and that resistance is going to be dissipating power. Okay, the power that we would prefer to be delivered to the cities and homes and not being dissipated as heat along those transmission lines. Okay, so let's just do some very simple calculations here. So remember that the power supplied is equal to the voltage of that power plant times the current that it's providing. Okay? So here I'm talking about the amount of power that's being delivered by the plant itself. Okay? So if that plant needs to deliver 10 megawatts to a city, then it has some voltage, and the amount of current that it has to send out will be determined by how much power it has to supply. So the larger the power that plant has to supply, the larger the amount of current that it needs to send out, okay, in order to provide that amount of energy, that power to the user. So that is the power that's being supplied. So the current will be determined by how much power that plant needs to provide. And then we have the amount of power lost or power dissipated. In the transmission lines, okay, and that we already calculated, I think I just erased it, will be equal to the square of the current that is flowing through the transmission lines times the resistance of the transmission lines. So that is the amount of power that is being dissipated as heat in the transmission lines just to deliver that power to the city. Okay? So, of course, we can limit this by decreasing the resistance, so either making the wires as short as possible, so moving the power plants, into your neighborhood, which there are a lot of proposals to do this, by the way, moving forward. So decrease the resistance, or decrease the resistance by moving it closer, or by using thicker and thicker wires, which decreases the resistance. But that gets to be prohibitively expensive in terms of making those transmission lines. So the other way we can limit the amount of power that's lost in the wires is to decrease this current. Okay? We can limit the lost power by decreasing the current. Okay? The smaller this current is, the smaller the amount of power that's lost in the transmission lines for a given resistance. So if we can decrease the amount of current that is flowing in the transmission lines, then we can limit the amount of power that's lost in the transmission lines. Okay, so how do we do that? Because we have a fixed amount of power that needs to be supplied to our city. Okay? So, but remember, the power delivered is the voltage of the plant times the current. So if we want to decrease the amount of current that is running through the transmission lines, but still deliver the same amount of power, we have to up the voltage. Okay? So we can deliver the same amount of power for a higher voltage running at a really low current. Okay? And that is how transmission lines actually function. So as we increase the voltage, we can decrease the current for the same power delivered. Okay, so those transmission lines that run power from the power plants are run at very high voltages. Okay, for very high voltage, you can deliver the same amount of power for a much smaller current. Okay, and then when the current is small, the amount of power that's lost in the power lines can be made very small as well. Okay, so just some numbers so you guys get a sense of this for transmission lines. Put that over here. So remember that our household voltage is about 120 volts. Okay? If the power plants were trying to deliver the voltage at 120 volts to our house, about 99.99999% of it would be lost in the transmission lines getting there. It would be an extremely inefficient process. Okay? So instead, they up the voltage on the transmission lines. So for long distance lines, these are the transmission lines, the power lines that you see on the big high metal towers. So they usually are running, you can see them running across the hills and stuff like that. So those are how they transmit over very long distance. The voltage is about, usually on those is about on the order of 100,000 volts. Okay, so a factor of 1,000 times larger than what's in your house. And then for the urban lines, so these are the power lines that are typically running on the transmission poles in your neighborhood. Those are usually lower. They have to start decreasing the voltages before they get it to your house, and those usually run around 20,000 volts. Okay, so but let's think about the difference between these two. The long distance line and the household voltage, there's about 1,000, factor 1,000 difference in the voltage. So that means that the current, when it's delivering the power, is about 1,000 times smaller for that transmission line, right, to deliver the same power. And then the amount of power lost goes with the current squared, okay? So that's 1 over 1,000 squared, which is 1 millionth. So you lose 1 millionth as much power by transferring it up to that high voltage, okay, before you send it along the power lines. And then, of course, they have to transfer it back down to lower voltages and higher currents once it gets to your house. Okay, so we're not plugging our laptops into 1,000-volt power sockets. That would be a little scary. So, okay, let's see. Any questions on currents and circuits? So this is the last of the material that will be on your midterm. Yay. Awesome. Okay, we will see you next time.